Hello all, welcome to part 1 of 2 of this lecture on igneous rocks. So this lecture is going to focus on rocks that are formed from magma that is cooled, whether under the surface or above the surface. And through understanding these different igneous rock types, we're going to try and use textures of rocks to tell how they formed and in what type of tectonic environment they formed, hoping that this can give us some clues as to how the world has rearranged itself in the past in terms of tectonic plates and volcanism. So our guiding question today will be to look at these 3 rocks you see on the screen now. These are all igneous rocks. They formed under different geologic conditions. So before we get into the lecture, I would like you to hypothesize the difference in the formation conditions based on the colors and the textures that you see in these rocks. I would like you to write this hypothesis down because we're going to revisit it at the end of this lecture and see how your thinking has changed. All right, so when that is written down, we'll move on. And in the first half, we're going to focus on where igneous rocks come from, where the magma is, and how the magma changes its composition as it moves through the earth. In the second half, we're going to focus on actually naming different rock types. So we'll first start out with magma sources. So magma originally is going to be sourced from the asthenosphere. And if you remember, tectonic plates are on the crust and the upper mantle. That is this rigid body called the lithosphere. The lithosphere sits on top of the asthenosphere. The asthenosphere is that deeper mantle. The asthenosphere is fairly uniform in composition with a lot of magnesium and iron within it. So if all molten rock and all magma comes from the asthenosphere, we would expect that all magmatic rocks, all igneous rocks, have the same composition. Yet, as we could tell a little bit from that opening slide, we see a range of colors. And so those colors are indicating something about the chemical composition of those rocks and showing us that there's actually a wide range of rock compositions for igneous rocks. So how does this happen if they all come from the same source? Before we get into that, I want to talk about 2 terms here. So I mentioned the upwelling asthenosphere is rich in iron and magnesium, and this is going to lend itself to a term that we call mafic. This is the composition that comes from the asthenosphere, and it's going to be the composition of some of these igneous rocks. So we'll call them mafic if they are rich in iron. And so you can think of that as ferric. So we're borrowing part of that word into mafic. And then rich in magnesium. So we're borrowing the beginning of magnesium into the term mafic. So these are going to be fairly dense. If you remember from last week when we talked about the composition of the earth, iron and magnesium are dense. That's why the mantle is denser than what lies on top of it. In contrast, when we look at the rocks that actually make up the continents, so kind of in this gray area on this diagram here, we see that these rocks are actually fairly rich in aluminum, potassium, silica, and oxygen. So this first half is going to focus on why this is. These aluminum, potassium, silica, and oxygen rocks are going to be called felsic rocks. So we're going to borrow from silica. We're going to create sic out of silica. And then aluminum, potassium, and oxygen are all elements that are common in feldspar rocks. And so we're going to take the fel from feldspar to combine and get felsic. So we're going to continue to use these terms. Mafic rocks are those that form closer to the mantle or the asthenosphere, and these felsic rocks are going to be in continental areas. We will also see some rocks that have both mafic and felsic compositions, and those will be called intermediate. And there are 2 main methods that we can go from that original molten rock source that is mafic into a continental rock that is felsic. The first of these is fractional crystallization. So this is a very simplified view of a volcanic plumbing system In reality, we would see a lot more kind of mixing and blurred lines between all of these volcanic vents and the magma chamber. So we'll look at in that magma chamber. So imagine that this mantle rock just kind of originally popped up. And if we took a close look at the elemental composition, we would see a lot of magnesium and we'd see a lot of iron shown here in red and in orange. There's also some silica and some oxygen as well, but there's still abundant magnesium and iron in this mantle. However, as this mantle is sitting here under the volcano, it is now a little bit further away from the warm, hot mantle, and so it is starting to cool. As the magma cools, magnesium and iron-rich minerals are going to crystallize first. So this just has to do with their chemical properties. At lower temperatures, at higher temperatures, they are less soluble. So you don't have to cross quite as low a temperature threshold to get magnesium and iron minerals to crystallize into their solid form. So these start to crystallize. As they crystallize, they fall as crystals to the base of the magma chamber, and they take out that iron and magnesium from the rest of the magma chamber. And so what we end up with after this initial cooling is a magma that is enriched in silica and oxygen compared to previously. There may still be some magnesium and iron left, but is much less abundant. And so you can see through this method that we are transitioning towards a more felsic composition. We often actually see this in magma chambers. So if you look at magma that's erupted in Hawaii, for instance, we will see what are called xenoliths. These are foreign rocks. And we see xenoliths within the magma that are composed of these really magnesium and iron rich minerals that crystallized and settled first. The other way we can change magma composition is through partial melting. So as you may have noticed, this magma chamber is not surrounded by more magma, it is surrounded by whatever rock is around it. And if it is in a volcano, that rock around it is going to be continental rock, which means that it is felsic. So as this magma is sitting here, heat is going to diffuse between these two rocks. So this process of diffusion that we talked about, landsliding, is also going to occur with heat. That's why if you turn a heater on in your house, eventually your whole house will warm up. You're not just going to have one hot spot in your house. So we start to see the surrounding rock melting up, and it's melting at fairly low temperatures at first. And at those low temperatures, we're going to see certain minerals starting to melt out initially. So at those low temperatures, the melt is mostly going to release elements of silica and oxygen. So just like it took iron and magnesium higher temperatures to cross that line between liquid and solid, silica and oxygen are going to take lower temperatures to cross that line. So during this initial heating of the surrounding rock, as it's just starting to warm up from cool temperatures, it's going to be that silica and oxygen that are added preferentially. If the surrounding rock continued to heat up, then we would start to see more iron and magnesium added to it. However, we often don't get to that case. So this partial melting preferentially will make the magma more felsic, right? So those are kind of the two main principles by which we get different magma compositions across the world. And we can apply these processes of magma differentiation to plate tectonics and predict where we would expect to see mafic and felsic magmas in relation to plate tectonics. And in reverse, we can kind of do the opposite of this process. If we pick up a mafic or a felsic rock, we can use that composition to try and reconstruct what the tectonic history was and what sort of plate boundary it was formed at. So for instance, we could reconstruct the formation of things like supercontinents. Okay, so let's think about magma differentiation with plate tectonics first, and then we'll do an exercise where we try and look at the rock types and back out plate tectonics. So when we think about the plates, we mentioned that there are oceanic and continental plates. Those continental plates will tend to be felsic, while oceanic plates will tend to be mafic. And this has to do with how much of the crust the magma has to go through and how much partial melt and fractional crystallization is occurring. So in general, though, oceanic plates will tend to be more mafic and continental plates will tend to be felsic. So if you imagine we have two subduction zones here, we have an oceanic crust colliding with another oceanic crust. And then at the bottom, we have oceanic colliding with continental. If we look at the melt that is forming and creating volcanoes, which one of these do we expect to be more felsic? So once you have an answer, we'll move on to the next slide. We would expect ocean continent to produce more felsic lavas than ocean. Right, so why is this? So both of these are going to experience some fractional crystallization as the magma is moving up through the crust, it's cooling and experiencing fractional crystallization. But in the case of ocean continent, there is this mass of felsic continental crust that is moving through, which allows it to experience some partial melting of that surrounding crust and adds more silica and oxygen to it. So we might expect that these volcanoes may be intermediate because they are still undergoing some fractional crystallization. So there is more of a tendency towards felsic composition rather than the straightforward mafic composition. But in the ocean continental, because we've had this added step of partial melting, we may expect these magmas to be felsic. So why does this matter? Well, as we talked about with volcanic hazards, viscosity is really important in determining whether or not we're going to have explosive eruptions, how far that lava can travel, whether we get things like pyroclastic flows or lahars. And that is all going to relate back to the composition. So mafic magmas tend to be a lot hotter, which makes sense because they're made of magnesium and iron. And if that magma cooled down, the magnesium and iron would crystallize out and no longer be there. So in order to be mafic, they by definition have to be hotter. And because they're hotter and because they contain magnesium and iron, they tend to be less viscous. So they flow easily. So Hawaii is an example of a mafic magma. We see the eruptions that come out of the Hawaiian volcanoes to be very flow-like. They're able to travel long distances and they contain those ropey, pahoehoe textures, which again indicate some flow and ability to flow. In contrast, felsic magmas are going to be more viscous. So they contain more aluminum, potassium, and silica and oxygen, all of which are kind of soluble at cooler temperatures, which is going to create a more viscous magma. Because they're more viscous, they resist flow and they tend to trap gases, which leads to more explosive eruptions, right? So as we talked about, that buildup of gases can increase the pressure in volcanoes and can result in really explosive and dangerous eruptions. So understanding those kind of plate boundaries and what magmas we expect to see is also going to help us inform what the expected hazards are, right? And just to kind of drive this home more, we can see an example of a mafic magma and its nice flow-like patterns. There's still some hazards there, but it's a little bit more predictable versus the complete blowout and pyroclastic flow and large flank collapse avalanche that occurred because of the buildup of gases at Mount St. Helens. So Mount St. Helens is a result of a ocean continent, and in particular, it's the oceanic Juan de Fuca plate, which is a small plate that mostly exists just offshore of Oregon and Washington. colliding with the North American continental plate. But Hawaii actually sits smack dab in the middle of a plate. So these mafic magmas and these eruptions we see on Hawaii aren't actually the result of plate tectonic dynamics. It's actually going to be a result of something called hotspot volcanism. And again, we kind of briefly introduced this idea in week 1 when we were talking about volcanoes. But hotspot volcanism is essentially we have a stationary plume of magma within the mantle. This plume does not move. However, it brings up hot magma and that infiltrates through the lithosphere and through the crust and erupts as volcanoes. These hotspots are stationary. However, they're interacting with plates that are moving. So just as we see in this diagram, because the Pacific plate is moving to the left in this view, it means that all of the old hotspot volcanoes eventually get moved over to the left. And so we get this nice timeline of volcanism of this hotspot where we know, 5.6 to 4.9 million years ago, the hotspot used to be under this part of the plate. And we know that the Pacific plate has moved this much in about 4.9 million years. So this is one way we can track plate speeds. We can also track the direction of motion. So the Hawaiian volcanic chain, when we look at the bathymetry, it actually has this interesting curve to it. So the Hawaiian chain follows this nice trajectory that kind of goes northwest, and then it switches to being more of a west-northwest trajectory, heading up more directly towards the Aleutian Islands. And so this switch here is actually indicative of a change in the plate tectonic velocity direction. So for a long time, the Pacific plate has been moving in this direction. However, about 48 million years ago, it switched directions. So it was, I have said that oppositely. So the plate was moving towards the north-northwest, and about 48 million years ago, it switched directions to be moving more directly northwest, right? And we can see that with these arrows here. Yeah, so this is a nice way we can reconstruct kind of globally what the plates have been doing. And this leads to some interesting questions. Why did the plate switch directions? And this may have to do, most likely has to do with interactions at the boundary of the Pacific plate. So maybe some switch occurred in which we suddenly had more of a slab pull or ridge push action that switched directions. So maybe a new spreading center opened up, we had a new divergent boundary, or maybe a new subduction zone started up and we had that renewed direction of slab pull. We can get hotspot volcanism in many locations though. So Hawaii and the Hawaiian volcanic chain is a really great example of hotspots within an oceanic plate. And because the mafic hotspot is interacting with oceanic crust, which tends to be mafic, the resulting volcanoes are mafic. However, we can also get hotspots in the middle of continental plates. So this is what Yellowstone is. We also have some hotspot like volcanism to the south of us in New Mexico. And here we do get things like partial melts occurring, and we get some fractional crystallization that is going to change the composition. However, we have a very interesting phenomenon here. So we have a very mafic hotspot that comes up, and it continually adds more mafic lava to this. So as this magma is kind of rising towards the surface, it goes through partial melting, and it gradually transitions to being felsic. And so towards the top here, we may have some felsic magma, and rhyolite is a type of a felsic rock. So when you see this rhyolite magma, that just means a felsic magma. But we have continued magma rising up from the hotspot, and that's going to be mafic. Basalt is a type of mafic rock. And what we end up with are magmas that are felsic and mafic. And you would think intuitively that these might mix and we would get an intermediate composition volcano. But it turns out that their viscosity differences are too great. So you can think of this as like oil and water. And they end up being immiscible, which means we cannot mix them. So we get bimodal volcanism at these hotspots where we may have mafic rocks and felsic rocks associated with the same volcano. I think that's pretty cool. And that is pretty unique to hotspots within a continental plate. All right, so now that we understand some of the settings, let's try and apply this knowledge. So can we look at rock type and figure out how the tectonic setting has changed over time? And we're going to focus here on the Pacific Northwest. This is an area that's fairly familiar to me, so I did my thesis PhD work in these areas. And it's fairly important, even though I think about erosion, it was really important to think about what the tectonic history had been, because that primed the rock types that I found there, and then those were subject to different types of weathering and erosion. So everything ties together, right? All right, so what we have here in this map are all of the igneous rocks that formed about 54 to 23 million years ago. In red, we have rocks that are mafic. Green and blue are felsic rocks. The blue are volcanic, so that means they erupted on the surface, whereas the green are plutonic, so they formed from a cooling magma chamber below the surface. So what kind of plate setting could produce these mafic rocks? And what kind of setting would produce these felsic rocks? Think about that for a second. And when you have an answer, move on in the video. Okay, so now that you have a hypothesis, let's test that. So mafic rocks tend to form in, we could say, we have ocean hotspots. Or we didn't really talk about this, divergent boundaries. So those are locations where the asthenosphere is directly upwelling into a boundary between two plates. And so it's not really traveling through a large plate. It's cooling a little bit and having some fractional crystallization, but remains mafic. And so we have mafic rocks erupting at divergent boundaries. And then because, the next, as that boundary pulls apart, those mafic rocks are now at the edge of the boundary. And so the next kind of pulse of magma coming up is going to interact with mafic rocks. And so it's going to stay mafic, right? Through partial melting, we're not going to get any enrichment in silica and oxygen. We tend to stay at this mafic level. All right, so these red rocks could be from a hotspot. They could be from divergent boundaries. These green and blue rocks are felsic. So that could be a convergent boundary, maybe an ocean continent. These could also be from a hotspot that is in a continent, right? We just talked about that bimodal volcanism. However, if it was a hotspot, we would expect to see that chain, much like we see with Yellowstone. We can see a nice chain of volcanism, or like with Hawaii, where we have that really nice defined Hawaiian volcanic chain. And here we don't really see that. Instead, over a fairly large spatial scale, we see the ocean hotspots or the mafic rocks kind of being separated from the continental rocks. So I'm going to use that as a way to eliminate this hypothesis, which means that our felsic rocks most likely came from a convergent boundary that was oceanic plate, ocean plate to continental plate. So then we have to turn to our mafic rocks and see if this was a hotspot or a divergent boundary. And again, we're just going to use some of the spatial relationships here to note that this is going to be a divergent boundary and not a hotspot. For one, we tend to see these rocks right here. And then if we go into Oregon, we can find very similar rocks in that location down there. And if we date these rocks, they're all about the same age. So we're not seeing progression like a hotspot. Like, so this was a hotspot, we should see the ages changing from south to north or north to south, or in whichever direction the hotspot was moving. So we don't see that. So that leads us to believe this was a divergent boundary, and it's next to some rocks that formed through a convergent boundary. And this has been used to back out that about 54 to 23 million years ago, where the state of Washington currently is now, there was actually a divergent boundary, much like we get in the middle of the Atlantic plate. And this divergent boundary was from two tectonic plates moving away from each other. And then very close to that, one of those tectonic plates was being subducted under another one, and that was forming this series of convergent rocks. So we can watch that evolution here. This is just a GIF showing the evolution of Washington state. So starting with 100 million years ago, we have these things called superterranes that are added on, but the Siletz crescent one that's in green here, those are the volcanic rocks that were formed in a divergent boundary. And they're juxtaposed with a series of volcanic rocks that run through the Cascade Range that were formed in a convergent boundary. We also have all of these interesting colors on here. These, what they call superterranes, these are island arcs. So the chain of volcanoes that result from an ocean-ocean collision produces a ring of volcanoes in an arc. We call these island arcs. And from the evidence of all of these insular superterrane and these other terrains in gray and in brown, we can tell that at some point, a bunch of these island arcs actually collided with the edge of the North American plate and became sutured or became part of the North American plate. So there's a lot to unpack here, but we'll leave it at that for now. And so that's going to be the end of part one, where now we've thought about how different magma compositions come to be. In part two, we'll switch to identifying rocks and get back at answering that initial question that we started with.